Hello guys, today's topic is the remaining part of basic inference are discussed here. Among them, first one is conjunction inference. In conjunction inference rule, we use different propositions, and this proposition is also known as a formula. You can say either P is a proposition or a formula. So P and Q, there are two formula or two propositions. If these two are true, then P meet Q is this P meet Q is also known as CN. Conjunctive normal. The rule is if there are a number of propositions like P, Q, R, then their CNF will be P meet Q meet R, and this formula will be true when P, Q, and R all are. This is the concept. There may be finite number of propositions. If there are finite number of propositions, you can add them either in left or right. But the rule is when all propositions are true, then this formula will be. This is the main concept of this inference. According to this figure, the formula is, the rule states if formulas P and Q are simultaneously, if P and Q both are true, then the formula P meet Q can be assumed to be. This is the concept. And if there are more than two, then they must be true. Then their conjunctive normal form or P meet Q meet all other propositions will be true. Next one is dilemma. Here P, Q, R, S. There are four different propositions, and they are related to P implies Q, R implies S, and P join R. All these three formulas are true, then you can say Q join S will be. To remember it, we can write here like this: P join Q, R implies, here P implies Q, R implies S, and P join R. All these three are true, then we say Q join S will be. If all these three are true, then this will be. To remember this formula, we say if there are two formulas like P implies Q, R implies S, then if their hypothesis, conjunction of their hypothesis is true, P join R, then their conclusion, conjunction of conclusion will be. This is known as hypothesis, as you know, and this is known as conclusion. In any P implies Q, P is a hypothesis and Q is a conclusion. So we can say if the hypothesis of given formulas, the conjunction of hypothesis of given formula are true, then their conjunction of conclusion will be also. Or simply we can say if the left side are, the conjunction of left side are true, then the conjunction of right side will be true. This is the concept of this dilemma. According to this, the formula is, the definition of this formula is, the rule states that if both the formulas P implies Q and R implies S are assumed to be true, and if P join R, that is disjunction of antecedent or hypothesis, is assumed to be true, then assume truth of Q join S, which is disjunction of consequence. In any given implies formula, in P implies Q, I have already discussed, the left formula or proposition is known as hypothesis, and antecedent, and this Q is known as conclusion, or it is also known as antecedent. Consequent. It is also known as consequent. So the definition is, the rules states that if both formulas P implies Q and R implies S are assumed to be true, and if P join R, that is disjunction of antecedent, they are antecedent, disjunction of antecedents is assumed to be true, then assume truth of Q join S, which is disjunction of. Now there are more inference rules. They are based on quantifier. Among them, the formula are universal instantiation rule UI, universal generalization rule UG, existential instantiation rule EI, and last one is known as existential generalization rule E. So as I have already discussed earlier, that universal quantifier is denoted by V like this, and existential quantifier is denoted by like. It means all, or it means some, not all. If all are true or all are accepted, then we use for all, and if any one among them is not correct or not taken, then we use their exist means some, and for all means all. So these two formulas, these two symbols are used for quantifier formula, and this universal instantiation rule is based on this symbol, and these two are based on this existential, but these two are based on for all. First one is universal instantiation rule UI. This rule says for all x px, then pa will be, if there is a formula that denotes that p is true for all x. If p is true for all x, then one element of that set pa will be true. If this one is true, then this will be true, where a is an arbitrary constant, and this, the value of this a will be the member of this set x. If we suppose x is a set of Ram, Mohan, Sohan, Ram, Mohan, Sohan. If the domain of x is Ram, Mohan, Sohan, then this a will be either Ram or Mohan, or the domain of x must be defined. If beyond the domain pa is pa will be not true, may be true or may not be. Okay, so the domain of x must be defined. Before saying this, that pa is this a must be the element of or member of the domain of x. This is the definition of this formula. Says the rule states if for all x px is true, then we can assume pa as true for any constant a, where a constant a is like Raman or any other name or number or anything that is the member of this domain x. It can be easily seen that the rule associates a formula pa of propositional logic of a formula for all x px of FOPL. FOPL stands for first order predicate logic. The significance of the rule lies in the fact that once we obtain a formula like PA, then the reasoning process of propositional logic may be, the rule may be used whenever its application seems to be appropriate means the A must be the member of the domain. If it is beyond the domain, then it may not be. Next quantifier based inference rule is universal generalization rule. It says if PA is true for all A, then we can say for all x px is true. If PA is true for all A, here it means if the domain of x is suppose A, it may be number, it may be name, it may be any other A, B, C, D. Then the domain of this x is A, B, C, D. And if A, B, C, D all are true for certain formula, then we can say for all x px will be. And if there is one more member like E and EA is true, then we can't say for all x px will be. These four must be true. I mean the domain of x must be true for each member, then this for all x px will be. So the definition is, the rule says that if it is known that for all constants A the statement PA is true, then we can instead use of the formula for all x PA. The rule associates with set of formulas PA for all A of propositional logic, a formula for all x px of FOPL. FOPL stands for first order predicate. Before using this rule, we must ensure that PA is true for all A, otherwise it may lead to wrong that I have already discussed in starting of this formula inference. Next inference rule is existential instantiation rule, EI. If there exists X, Px is true, then PA will be. The definition says, the rule says if the truth of there exists X, Px is known, then we can assume the truth of PA for some fixed A. The rule again associates a formula PA of propositional logic to a formula for all X Px of X. So, if some X is true, then PA will be. Next one is existential generalization rule, EI. If PA is true, it means A is a member of the domain of X, and it is true, then we can write, we can say there exists X Px. Here, X, suppose the domain of X is A, B, C, D, then A must be the member of among these numbers or symbols. A must belongs to the domain of X. Then if A belongs to this domain, then we can say that there exists a Px. So if PA is true and A belongs to this domain, then we can say this one is. The rule states that if PA, a formula of propositional logic, is true, then the truth of there exists XPX, a formula of FOPL, may be assumed to be. If the upper part or nominator is true, then denominator will be. So these are all inference basic rule.